Mba633 instructional video prepared by Professor Amit Datta, School of Management, George Mason University. In this segment, we will be discussing confidence interval for the population mean. How does one go about making inferences about the population mean? So the situation that we have here is that we want to find out the average time taken to fill out the federal tax return. So the population here is the set of all federal income tax filers, the millions of them, and I want to know the average time taken to fill out the tax returns. And based on historical data, we are told that the standard deviation, the population standard deviation of the time taken to fill out the tax returns is 9 hours. Now, it's not common to know the population standard deviation, but we will see later how to deal with it. Since we are just starting our discussion of confidence intervals, we'll be assuming that the population standard deviation is known, and in fact there are circumstances where it is known. Okay, so it's not just a made-up situation. So given that the population standard deviation is 9 hours, in this case the time taken to fill out the federal tax return, I want to get an estimate of the average time taken to fill the tax return. So what do? I took a sample of 40 individuals. I asked each one of them how long it took to fill the tax return, and I computed the average of the 40 numbers they gave me, came up with 33.5 hours. So that one number, 33.5, is the point estimate of the population mean. So if I had to give you one number which is my best estimate of the average time taken to fill the tax return, I would say 33.5 hours. But I can't really tell you how certain am I. I know I might be close, but I don't know how certain. So with confidence intervals, what I'm saying is don't give me one number. Give me a lower limit and an upper limit. Okay, so that I have a certain level of confidence that the population parameter I'm looking for, in this case the mean, lies between those two ranges. So if I had to give a narrative, the confidence interval would read like this. I am 97% sure that mu lies between x bar, which is the sample mean, plus or minus a margin of error. Okay, so the lower limit is the sample statistic minus the margin of error. The upper limit is the sample statistic plus the margin of error. So the whole issue is how large does the margin of error have to be. Now you can see that there are three things going on here which have to be traded off. Okay, one is the margin of error. Okay, one is how sure I want to be, what level of confidence I'm willing to I need, and the other is the sample size. I think you can easily guess intuitively that other things remaining constant, if I want to be more certain, but I'm not willing to yield on the sample size, I have to tolerate a larger margin of error. On the other hand, if I need a fairly small margin of error, but I also want a high level of confidence, I have to go for a much larger sample size. Why is it? Because you go back to our sampling distribution of the sample mean. Remember the central limit theorem, which said that for large sample, which means in this case a sample size greater than or equal to 30, which is true in this case, the sample size is 40. We know from the central limit theorem that the sample mean is normally distributed with a mean equal to the population mean that I'm trying to estimate, and the standard deviation of the sample mean. Look at this, the symbol here. There are a lot of sigmas floating around, so don't get confused. It says sigma with a subscript of x bar. So this is the standard deviation of the sample mean. And we know from our prior discussion of sampling distribution, this is equal to the population standard deviation divided by the square root of the sample size. So the larger the sample size, the skinnier this bell. So more certain I am about where my sample mean is, or how close it is to the parameter that I'm trying to estimate. So in this case, the standard deviation of the sample mean is simply 9 divided by square root of 40, which turns out to be 1.43 hours. So that's one standard deviation of the sample mean, how large that is. Okay, notice that this is not the standard deviation of the population. This is 1.43 is the standard deviation of the sample mean. It depends on the sample size, as you saw from the expression over here. Now the question is, how large should this margin of error be? Since I want to be 97% sure, the margin of error has to be large enough so that this yellow shaded portion under the bell-shaped curve between L and U between the lower limit and the upper limit has to be 97%. Okay, so I want to be 97% sure. So how much does that leave in the two tails? So one tail, and here's the second tail. These two tails together is 3%, isn't it? Because the yellow shaded portion is 97%. So what is the area to the left of U? In other words, this yellow shaded portion plus this green shaded portion. So the area to the left of U would be equal to 97% plus 1.5%, isn't it? Because the two tails together is 3%. So the green half on the left is 1.5%. So it's 0.015. So in other words, the area to the left of U is 0.985. Why am I so concerned about getting the area to the left? Because that is what the Excel built-in function norm inverse, norm this, norm s inverse, norm s this, all those needs, you know from a discussion of those built-in functions. So what does U need to be such that the area to the left of U is 0.985? So we would use the norm s inverse in this case. Since I know the probability and I want to know my position on the x-axis, so let's do that. S norm s inverse, and you can see it only needs one input. What is the probability? Is 0.985. Okay, and I hope you see where the 985 came from, even though I want to be 97% sure. So this is 2.17. So what is the physical interpretation of 2.17? The physical interpretation of 2.17 is that if I want to be 97% sure, then my margin of error, this margin of error has to be 2.17 standard deviations wide. Why? Because you remember I used the standard normal norm S inverse built-in function, isn't it, to calculate the 2.17. So my margin of error is 2.17 standard deviation. But I know that one standard deviation is 1.43 hours. So my margin of error in hours is simply equal to 2.17 multiplied by whatever that one standard deviation was, is 1.43. Okay. So this is equal to, let's do the computation over here. It's equal to 2.17 times 1.43, so it's 3.1 hours. Okay, therefore my confidence interval is equal to 33.5 plus or minus 3.1 hours. So I can complete my inference by saying, instead of giving a simple point estimate, hey, it's 33.5 hours and I'm not sure how close I am, instead of saying that, I'm saying I'm 97% sure that the average time taken to fill out the federal tax return lies between 30.4 to 36.6 hours. Okay, so I hope you see where the range came from. So it's the sample statistic plus or minus a margin of error. So the general mechanics of computing standard deviations is try to link first that how sure you want to be, in other words the level of confidence, with how large the margin of error has to be in standard deviations. Once you know how large the margin of error has to be in standard deviations, then all you have to do is multiply it by how large one standard deviation is. Okay, that's why we multiply 2.17 by 1.43. So if I want to be 97% sure, the fact that the sample mean is distributed normally with this standard deviation, it tells me that my margin of error has to be 2.17 standard deviations large. And since one standard deviation is 1.43 hours for this specific problem, my margin of error for this specific problem is 3.1 hours. Hence, I am 97% sure that the average time taken to fill out the federal tax return is 33.5 plus or minus 3.1 hours. In other words, between 30.4 hours and 36.6 hours. Okay, so this is how one goes about computing the confidence interval for the population mean, provided the population standard deviation is known. In the next clip, we will see what you do when you don't know the population standard deviation.